Welcome to an exploration of programming paradigms for software developers. We're setting off on a journey to understand the conceptual frameworks that guide the way we approach coding. These are the paradigms that influence how we structure, how we organize, and how we view our programming tasks. Programming paradigms are like the blueprints of software development. They define the methodology we use to solve problems, helping us to write code that is efficient, maintainable, and easy to understand. They provide a way to categorize different styles of programming, each with its own set of principles and techniques. Let's start with an overview of what these paradigms are. The first one on our list is the object-oriented programming, commonly known as OOP. OOP is a descendant of procedural programming, which is another important paradigm. The shift from procedural to object-oriented programming introduced a new way of thinking about code. Instead of focusing on the steps needed to perform a task, OOP encourages us to think in terms of objects and their interactions. This shift brings code closer to how we perceive the real world, where we interact with objects that have properties and behaviors. In Java, you see OOP in action every time you create a new class or use inheritance to share code between classes. It's a way of organizing data and functions into units called objects, which can be manipulated to perform tasks. The focus is on the data, and the procedures are secondary. However, OOP is not the only game in town. As we continue this journey, we'll explore other paradigms like procedural programming, functional programming, and declarative programming. Each of these paradigms offers a different perspective on how to write code, and understanding them can give you more tools to tackle programming challenges. Stay tuned as we delve deeper into each paradigm, starting with the popular object-oriented programming. Jumping right in, let's examine object-oriented programming, or OOP. This paradigm is like a car factory assembly line, where different parts come together to create a complex machine. In OOP, these parts are objects, instances of classes, that interact with one another to build a complete program. Let's start with encapsulation, one of the core concepts of OOP that involves bundling of data, variables, and the methods, functions, that operate on that data into a single unit, typically a class. Encapsulation allows us to hide the inner workings of a class and expose only what's necessary, promoting data integrity and security. Next, we have inheritance. Picture a family tree. A child inherits traits from their parents, right? In Java, a child class or subclass can inherit properties and methods from a parent class or superclass. This means we can create general classes and then extend them to make more specific ones, promoting code reusability. Now let's talk about polymorphism. In Java, an object can take on many forms depending on how it's used. This allows us to write flexible code where objects can be interchangeably used, promoting code flexibility. To illustrate, let's consider a simple Java example. Suppose we have a superclass animal with a method makeSound. We create subclasses dog and cat, each overriding the makeSound method. A dog object will bark, and a cat object will meow, demonstrating polymorphism. So far, we've seen how OOP focuses on objects and their interactions, encapsulating data and behavior, promoting inheritance for code reusability, and leveraging polymorphism for flexibility. It's a powerful paradigm widely used in Java that brings a real-world perspective to programming. Now that we've got a grip on OOP, let's move on to procedural programming. Next up, we have procedural programming. Picture yourself in a kitchen, following a recipe. The recipe, like a procedural program, is a series of step-by-step instructions. You, the computer, execute these instructions in the order they're given. This, in essence, is what procedural programming is all about. Procedural programming is an imperative programming paradigm, based on the concept of procedures, also known as routines or subroutines. A procedure contains a series of computational steps to be carried out. This paradigm allows you to break down a larger program into manageable procedures, or functions, each of which handles a specific task. One of the key characteristics of procedural programming is its emphasis on the separation of what should be done from how it should be done. This means that the focus is not just on solving the problem, but also on how the solution is organized and structured. Let's illustrate this with a Java example. Suppose you have a program that calculates the area of a rectangle. In procedural programming, you might have a procedure named calculateArea that takes the length and width as parameters and returns the product of these two values. This procedure solely focuses on how to calculate the area, while the main program decides what to do with the result, whether it's to display it to the user or use it in further calculations. Another important aspect of procedural programming is the organization of code versus the algorithm. In procedural programming, code is typically organized into procedures or functions. These procedures are designed to perform specific tasks and can be called from other parts of the program. The algorithm, or the sequence of steps to solve a problem, is encapsulated within these procedures. This makes it easier to understand the flow of the program and debug it when necessary. In conclusion, procedural programming is like a well-written recipe. It provides clear instructions on what to do and how to do it, making it easier to follow and less prone to errors. It's simple, straightforward, and effective, making it a great approach for many programming tasks. Having seen the procedure, let's now shift gears to functional programming. Now, let's dive into the world of functional programming. Functional programming, a paradigm that's been around for quite a while, takes its roots from mathematics. It's organized around the concept of pure functions, avoiding shared state, mutable data, and side effects. This is a stark contrast to the way we've been thinking about code in terms of objects and procedures so far. In functional programming, the output value of a function depends solely on the arguments that are input to the function. So, if you give a function an input of x, it will always return y. It doesn't matter what happened before or what's going to happen next, the function is only concerned with its input and output. This might feel a bit alien, especially if you've been living in the world of object-oriented programming, but don't worry, it's less complicated than it seems. And believe it or not, Java supports functional programming, even though it's traditionally been more associated with object-oriented programming. Java 8 introduced lambdas and streams, which are tools that allow us to write functional-style code. Lambdas in Java are essentially anonymous functions that we can treat as values. We can pass them around, put them in variables, or use them as inputs and outputs for other functions. Streams, on the other hand, provide a way to work with sequences of elements in a functional manner. They can be used to perform complex data processing tasks, like filtering, mapping, or reducing, in a declarative way. Let's take a simple example. Suppose we have a list of integers and we want to find the sum of all even numbers. In a procedural way, we might loop through the list, check each number, and add it to our sum if it's even. But with streams, we can simply filter out the odd numbers and then use the reduce function to get the sum. It's more concise, easier to read, and less prone to errors. With functional programming covered, let's explore the final paradigm, declarative programming. Finally, we arrive at declarative programming. This paradigm is unique as it emphasizes what needs to be accomplished without getting tangled in the how. It's like writing a to-do list, where you outline what you want to achieve without detailing every single step. In declarative programming, we focus on the logic of computation, not its implementation. It's all about expressing the logic of a computation without describing its control flow. This approach offers brevity and simplicity, as the programmer only needs to state the desired result, not the step-by-step process to achieve it. However, like every coin has two sides, declarative programming also has its trade-offs. While it provides simplicity and ease, it can sometimes result in magic code. Code that works but is hard to understand or debug because the implementation details are hidden. Imagine having a to-do list with tasks like, build a spaceship. Sure, it's a clear goal, but without the how, it could leave you scratching your head. Now let's take a step back and look at the bigger picture. We've journeyed through different programming paradigms, each with its unique approach and methodology. We started with object-oriented programming, the assembly line of the programming world, where we encapsulate data and methods into objects. We then explored procedural programming, akin to following a cookbook recipe, where we separate what needs to be done from how. Next, we delved into functional programming, which is like solving a mathematical equation, organizing our code around pure functions. And finally, we've just unpacked declarative programming, the to-do list of programming paradigms, where we state what we want without the nitty-gritty of how. Each of these paradigms offers unique perspectives and tools that you can apply in your Java projects. Remember, the best software developers aren't afraid to experiment with different paradigms. So go ahead, explore, and expand your Java knowledge.